yeah, thanks first of all to the organizers. For the invitation to speak. And let me start with this caveat. So, because of the mixed audience, I try to do my best in preparing the talk to please all the physicists and the philosophers. And the way I've done it is by having very, very little mathematical technical details in order to please the physicists that are, that bother with them, every day in their week, working week, and to be philosophically naive enough to amuse the philosophers. So I hope you appreciate that. So in the old talk, I'm going to almost equate the problem of time in quantum gravity with the problems of emergence of space and time in quantum gravity. So on the one hand, I'm putting together space and time because I frankly do not know of the quantum gravity formalism, at least of the ones I work with, that really treats the two in very different ways. And for me, the two problems of emergence of space and emergence of time are really related, so it's hard for me to treat them separately. And the other thing that this identification assumes is that space and time do disappear in quantum gravity. So from a certain perspective, I'm assuming an answer to one possible question, what happens to space and time in quantum gravity, because but that seems to me the obvious, the natural situation, and the formulas that I will refer to, that's indeed what happens, as I will try to argue. And for me, the real problem is to make space and time, as we know them, so continuum notions of space and time, emerge out of whatever else our quantum gravity theory is based on. So this is just to clarify the perspective. And the whole purpose of the talk is to not solve any issue, but to create more trouble. So the purpose is to show that the issue of disappearance of space and time and of emergence of space and time in the opposite direction actually has three levels. While we usually only consider the first one, actually I will try to argue that we only consider the zeroth level. So if you understand what I mean by the three levels, by the end of the talk, well, then I fulfill my goal. And at each level, there are new conceptual issues, which for philosophers, and I think for physicists alike, are opportunities. And I'm going to try to highlight all these new issues and opportunities. Again, as a general setup, I say something that probably obvious for some quantum gravity theorists, especially those coming from a particle physics approach, and take really seriously the fact that if you try to quantize general relativity around flat space as zero gravitons, you see that it's non-normalizable, and from that point of view, it cannot be taken seriously as a fundamental theory. And one can draw a more general lesson that general relativity cannot be considered a fundamental theory, period, regardless of how you try to quantize it. New degrees of freedom are needed, and it can at most arise as an effective field theory out of something else. At this stage, at the very beginning of the talk, I'm not sharing this point of view. I'm not necessarily agreeing with this point of view, but indeed I want to stress that quantum gravity is at least not necessarily and certainly not only about quantizing GR. By the end of the talk, you will actually, I will give it away, and you will see that I actually do agree with this point of view, and indeed in the approaches that I'm going to discuss, it's very hard to say that what they do is just to quantize GR. And that is exactly what gives rise to the three levels of emergence for space and time that I'm trying to discuss. So the goals of quantum gravity, from the perspective I'm adopting here, are a bit more general, and you may say even more radical. So the goals are to identify what are the fundamental, or at least the more fundamental degrees of freedom underlying space-time, what you can pictorially call the atoms of space, or the atoms of space-time, depending on the view. To define a consistent quantum dynamics for them, and that's the concern of the talk, to show that a continuum and then classical space-time emerges out of them in some approximation. In the process, or immediately afterwards, you should show that GR is a good effective description for the dynamics of such emergent space-time. So, level 0, which is basically the problem of time as it is usually initially phrased, and it is the view from quantum gravity as quantum GR. In the classical theory, we know we have a manifold, a metric, an action, the metric, the Einstein-Hilbert action, or you prefer some modified gravity action, or some higher derivative action for GR, for the metric, and the Einstein's equations. Plus possible other terms if you started with a modified gravity action. And you're in a smooth manifold, and so on and so on. And the whole problem of time from the point of view of quantizing GR, of quantum GR, is already there in classical GR. Frankly, it's hard for me often to tell what really is new about the fact that time disappears in a quantized version of GR. So, and the problem is, you can say it relates to different variants, but it's really a physical thing. So this neither, is the point that neither the dynamics of the theory, the action, the equations of motion, nor generic solutions of that dynamics have a preferred time direction. And there's no reason to expect it. Some particular solutions may have indeed preferred time directions, but it's a feature of specific configurations, specific solutions. Locally, of course, you can say in a system-dependent way, you can identify equally valid notions of time. But this infinity of equivalent possible definitions of time locally is the statement that there's no preferred time. And that's the classical version, for how I understand it, of the problem of time in classical geometry. So the two things I want to notice, this is all known to everyone. I'm not saying anything particularly original or clever. So the two things to notice is, first of all, it's exactly the same for space in GR. The mathematical and physical situation is identical. There may be, of course, conceptual issues because conceptually time is a more fundamental notion and so on. But from the point of view of what the theory is telling us, is not treating the two in a different way. And we cannot ask the theory to solve the problem of time if it doesn't solve the problem of space as well. And the other thing I want to say that may be a bit more controversial and may need more qualifications is the fact that I don't see, at least at this stage, any essential difference if I work in a canonical or in a covariant path integral-like formulation. I'm aware that the path integral formulation of a quantum theory, even assuming standard quantum theory, is more general than the canonical one. In particular, you cannot set up the initial definition of a phase-space variables in canonical analysis if you don't have an hyperbolic manifold, so it restricts a bit the topologies. But the point is that if you have a canonical formulation, everybody expects that you can equivalently rewrite everything in a covariant language. So in any case, let's take it as a methodological point. In the rest of the talk, I'm going basically not to differentiate between having a canonical or a covariant formulation of your favorite quantum theory of gravity. When you move to the quantum theory, still in this quantum gravity as quantum GR perspective, you have Hilbert space, you have a dynamical constraint equation, or in a path integral language, you're going to have transition amplitudes, which are just would be just a scalar product in the Hilbert space, in the physical Hilbert space from the canonical point of view. But you can write them in a sum of histories language. So at this stage, the situation is just the same. There's no preferred time direction, and as a result, there's no preferred time derivative in the dynamical equation. So the situation is just the same, only worse. And it's worse only because although the origin is the same, and physical nature of the coordinates, no preferred time directions anywhere in the generic configurations or in the dynamics, it's worse just because having a preferred time direction is essential in our formulation and understanding and interpretation of quantum theory. So from that point of view, it's true. You can, even if you blindly apply quantization methods to GR and get to quantum GR, you may have a formally well-defined theory, but you have to be much more careful, and you have some additional difficulties in interpreting the objects you define, because in the usual treatment and interpretation of quantum theory, we do rely on the existence of a preferred time direction. It's just that I don't want to blame the theory for that, or nature for that. I would rather blame ourselves. Okay. So it is true that even in the case of quantum GR, we are a bit at loss. But as I said, it's more of a problem of understanding if there is a better foundation of quantum theory once you include general covariance and gravitational dynamics than a problem with the absence of time, because otherwise you should worry already at the classical level. Okay. And in increasing order of potentially controversial statements, I'm going to say that, for me there is a very natural solution of the problem of time in classical or quantum GR. It has been already mentioned in some previous talk by somebody that I don't see. And is the notion of relational time. And of course, there are again some conceptual issues still left over once you use this framework. There are still technical issues and so on, but it just comes very physical to me. There's no time in nature in the sense of a preferred time direction, and in fact we never observe one, we never use one, we never see one. What we see and use are clocks. So rather the problem in any physical theory is to identify a subsystem that plays a good role as a clock, that you will use to label, to parameterize the evolution of the other degrees of freedom of the theory. Again, I don't want to say that this is the final word, because it's not. There are still conceptual issues and there are many technical issues. From this point of view, first of all, it's not given that you can find a clock in your specific quantum state, in your system. And even if you find it, it's almost sure that it's not going to be a perfect clock. At the very least, because it's going to be a quantum system itself. So of course there are many remaining issues. But at this level, which my point is still level 0, this is an acceptable working solution that settles the main conceptual picture as far as I'm concerned, and leaves me with fixing all the remaining issues. But from the general conceptual perspective, I'm more interested in going to level 1. So, in order to show you why in a sense, we are forced to go to level 1, I tell you what is the theoretical context in which I work, and where we stand more or less in this framework, in this context. So let's start from loop quantum gravity, which you probably understand as the most conservative, boring way of trying to find the theory of quantum gravity, which is exactly what I said is not necessarily the case. Quantum gravity obtained or attempted as TGR quantized. Conceptually, there's not much more than that at the beginning, except that you're serious about it. And so you really take GR with all its symmetries, different variants and so on, you take them for what they give you, and you keep going. Of course, there is a change of variable from metric variable to Ashtekar variables, but from the point of view of the workshop with philosophers, these are to a large extent technicalities. However, they end up not being technicalities because of the consequences. So in two steps, I mean, what you do, you start from, you want to quantize GR rewritten in this connection and triad variables, canonically. But then, in order to make things well defined and to transform nicely with respect to diffeos, and with respect to the local gauge group of gravity, which is the Lorentz group, you go to some discrete counterparts of connection and triad. You work with a different set of variables on phase space, which are the holonomies of the connection, basically the parallel transport of the connection along all possible paths in your spatial manifold, your canonical hypersurface, and the fluxes of the triad field across surfaces. So again, details are not so important, but all this is defined in some embedding manifold, very traditionally, and but you end up with group elements as variables rather than fields, group elements associated to lines, and the algebra elements associated to surfaces in that manifold rather than fields. So you go to certainly a set of non-local or less local variables. Now, I'm cutting 25 years of developments, but you impose diffeos, you keep going with the quantization program a la Dirac, for what you can, and what I'm interested in is the endpoint, the current endpoint of the story. You end up with a Hilbert space with a set of quantum states of degrees of freedom for your quantized gravitational field, which are purely algebraic and purely combinatorial. Basically, also the information about the initial embedding manifold and so on is lost. It's basically gone. You end up with a Hilbert space that decomposes. What I wrote in that line there is not exactly technically correct. I can go and explain what extra conditions you have to impose, but that's the picture. So you have a Hilbert space that decomposes into a sum over Hilbert spaces associated to graphs. All possible graphs you can hook up. With a Hilbert space for each graph, which is based only on degrees of freedom from the SU2 group, or the Lorentz group in a more covariant formulation of the theory. So purely algebraic data, labeling purely combinatorial structures. Algebraic data, group elements or group representations and so on, labeling graphs. And you can find a basis which makes this even more clear, the spin network representation for your quantum states, in which your orthonormal basis elements are indeed graphs labeled by representation labels from SU2 spins. That's what a quantum state of space looks like in the theory at the end of the whole story, even though you start in a very conventional, conservative way. And then, you have the problem of the dynamics, and you can keep going in the canonical way, try to impose some operator equation that plays the role of the Hamiltonian constraint equation on your quantum states. And then, depending on your perspective, how much you stick to the initial, quantizing GR perspective, then you choose an operator that comes more or less directly from continuum classical GR or not. But the formalism is clear. You have to impose a constraint equation, and it has to be a constraint equation just because you don't want to reintroduce a notion of time that has no place either in the classical nor in the quantum theory. Or in a covariant definition, you may go for a sum over histories formulation. But again, by construction, because your fundamental degrees of freedom of space are algebraic and combinatorial, a history is going to be algebraic and combinatorial. So instead of having a graph labeled by representation data from the Lorentz group, you're going to have a two complex. Think of it as the evolution, the history of a graph that can change the combinatorics as well as the labels, labeled again by the same type of algebraic data. This is called the spin form. And then you write down your choice of model or your construction principles give you an assignment of amplitudes to these histories. And you have a sum over histories definition of the dynamics, where you have a sum over all possible labels, algebraic labels, associated to these two complexes, and a sum of all possible two complexes, not the sum of histories. But again, it's a sort of purely combinatorial and algebraic version of a would-be continuum path integral for 4D geometries. Okay. That's the only point I want to make about the context. Of course, there are many open issues, and I can tell you what we know, what we don't, what are the open problems, what we have no clue how to solve, what we have basically solved, but there are some remaining technical issues, or what is done and once and for all. I want to move one step farther from the original point of view of canonically quantizing GR, even farther than where we already got in loop quantum gravity, in the sense I just explained, and tell you something about group field theory. So it's another formalism, and there are many ways to interpret it. It's another formalism for quantum gravity. You may interpret it in many ways and justify it or motivate it in various ways, coming from matrix models, from 2D gravity and string theory, from lattice gravity. I mean, there are many ways. Let me motivate it coming from loop quantum gravity, which is in many ways, I think, the best way to understand it. So formally, I'm just trying to write down a quantum field theory for a field defined on a group manifold, which could be, so it's actually several copies of a group manifold G, D copies of a group manifold. For models that are related to loop quantum gravity, the group is SU2, and the number of copies is 4, if you're interested in four-dimensional gravity, four-dimensional space-time. And the best way to understand it, coming from loop quantum gravity, is a sort of a second quantized version of the same story. So, in this is a field theory for the same type of states that you arrive at from loop quantum gravity. Generic spin networks, spin network states from loop quantum gravity become, in this field theory, basically many particle states, like many objects, many body states. And the particle, the individual, the single quantum of the field can be associated to a spin network vertex. So it's a bit like I gave you a spin network state from loop quantum gravity. It's a graph based on a graph with 4 trivalent, say, vertices. And I split it in 4 components, 4 constituents. Those are the 4 particles that make up the corresponding state in the group field theory formalism. Okay? So you can start defining the theory perturbably around the Fock vacuum for the field theory. But this Fock vacuum has no space-time interpretation at all. It has nothing. There's no space-time structure, no topology, no geometry, nothing. And then you start creating quanta. Creating quanta with this in this field theory means that you start creating spin network vertices, which can also be written pictorially, again, as simplices, like tetrahedra or high-dimensional cells. And just to make clear, I mean, the quanta of space-time in this picture are tetrahedra, same, in the same pictorial only sense in which an electron is a spinning top. Again, you draw it as a spinning top, but you're just capturing some properties of the system, but it's not that the world is made of little spinning tops here and there at the quantum level. And a generic quantum state is just many particle, many quanta state of the same type, glued or not. So you can have open graphs, closed graphs, and so on. Okay. So it's a quantum field theory of spin networks. That's the basic understanding you need at this stage. You then choose your model. Again, you tell me you have your construction principles, you have your criteria, either inspired by continuum GR or coming from a different source. And you write down your favorite dynamics, your model. And because of the peculiar way in which the interactions in this type of field theory are combined, are defined, there is a very general consequence that when you write down the quantum theory, initially you try to define it as a sum over Feynman diagrams around the Fock vacuum. so perturbatively in the coupling constant of the interaction there, what happens is that the Feynman diagrams are dual, not to graphs, but to cellular complexes, high-dimensional combinatorial structures. And more than that, in the models that have to do with quantum gravity, the amplitudes that you associate with these complexes are exactly the spin foam models you may have defined from the canonical point of view.
What are you integrating over in the action? Sorry, this is...
Sorry?
What are you integrating over in the action? Is it like a group manifold? Or?
Yeah. All the variables of the field are group elements.
Okay.
And is that a local action? Is the action local?
It's non-local. So when I say combinatorial non-locality, I mean something like this. I mean that I take a field which has like, say, 3 group elements, another field which has like 3 group elements. So each field would be like, for example, normally we use 4 group elements, but let's take a simpler case. This would be the analog of writing x, y, z.
Right, so this looks like a multiple non-local interaction
so
term.
one field like that.
The kinetic term looks local, I think.
Yeah, the
but
kinetic term is a standard
interaction term is
quadratic
not.
local term.
Okay, good.
And the non-local term is such that one example is this type. You identify or combine the elements, the variables in your fields in a combinatorial non-local pairing. If you know about matrix models, this would be exactly the generalization to higher dimensions of a matrix model from the combinatorial point of view.
Yes. Okay.
Matrix model would be the 2-dimensional case. And in fact, as I mentioned briefly at the beginning, you can arrive at this type of formulas coming from matrix models and just trying to generalize to 3, 4 higher dimensions.
That's true, but a matrix model doesn't have a non-local interaction term, does it?
It does. Simplest matrix, from this point of view, let me clarify what I mean by non-local. I mean this non-local pairing of arguments. So this would correspond to taking a matrix Ij, add to a matrix K and Ki. This is exactly this pairing.
Right, but that's a trace of local operators in the sense of the quantum field
It's
theory.
local in the sense of the matrix model, in the sense that it is unitary. That you have a unitary transformation on each index. If that's your definition of locality, then those terms are local and you can choose your interactions there, again, according to a UN invariance. But what I mean is that from the point of view of a standard field theory, I would take the x variable in one field and just identify with the x variable in the other and the x variable in the third field, and the same is for the y variables. So they would be all identified. This is what I mean, combinatorially local versus combinatorially non-local.
Thank you.
Right. So as a consequence of that particular way of combining arguments, just like in matrix models, the Feynman diagrams are not graphs, but higher dimensional combinatorial structures. And whatever was your summary histories dynamics in loop quantum gravity, your spin foam model, you can encode it as the Feynman amplitudes of a corresponding group field theory. That's the connection with that line of work. So it has the same type of degrees of freedom, but there is a shifting interpretation and there are some technical differences that I'm not going to delve into, because they're not crucial for what I'm going to say in the following. But so take it at this stage just as a field theory for the same type of degrees of freedom that you found in loop quantum gravity. The shift interpretation may be more relevant for the audience, that in this formalism, really you're taking more seriously the discrete structures as they were like fundamental objects. They don't really organize them as if they were necessarily coming from some continuum field that you discretized or something like that. you take them really seriously. You take them tentatively as the true atoms of space. And the group field theory is your candidate for the quantum field theory formulation of the dynamics of those atoms. From this changing perspective come also a certain set of new tools and ideas. So for example, it makes almost immediate to apply tools on renormalization, Wilsonian renormalization and so on. You have a field theory with a well-defined Fock space. It's a field theory on a certain manifold, the group manifold, even though it's not space-time. It's a manifold, so you keep applying, you can just apply all the standard technical tools from renormalization with some minor adaptation. And also you really may take and follow more closely the condensed matter analogy. You can really decide to take seriously this pictorial view of the group field theory as a quantum field theory for the atoms of space, out of whose collective behavior space should emerge. And this is what I'm going to discuss in the following. So the first main point is that no matter how conservative you start, and one can argue that string theory started in a conservative way, although from a different perspective, you end up with something radical. Apparently just trying to combine GR and quantum mechanics lead you to something radical, even if you don't want to. So space-time really dissolves into degrees of freedom that are hardly geometric or spatio-temporal. As a result, space and time had to emerge from their collective quantum behavior. So space and time dissolve. I couldn't find a better way to represent that. It's not mine, by the way. I want to take credit. So you end up with new non-geometric and non-spatio-temporal physical degrees of freedom, your building blocks for space-time. And then immediately comes a new question. You have a new direction to explore, which is the number of such fundamental degrees of freedom. What happens when you pile up more and more of such interacting quantum degrees of freedom? And it's the same question that you would ask in condensed matter. You have the atomic field theory. What happens when I start considering more and more of them? And it's natural to imagine that the space-time will emerge in the regime of large number of such degrees of freedom. And the second main point I want us to keep in mind is that the physics of few degrees of freedom is very different generically from the physics of many degrees of freedom. This is even one more reason why, even though you may have arrived at this type of structures from trying to canonically quantize GR, not only they're different, but the physics of many of them is probably going to be much richer than whatever you imagined as a starting point. So there are new collective phenomena and so on. So quantum gravity approaches are indeed learning to move in this new direction. And I like to call it the Bronstein hypercube of quantum gravity. I don't know if you know about the Bronstein cube, with the three main directions of relativity, quantum mechanics, and special relativity, quantum mechanics, and gravitational physics. But the fourth direction is the number of your fundamental degrees of freedom. And it means that we really have to take seriously the three main lessons coming from the three main areas of theoretical physics: GR, quantum mechanics, condensed matter. Anyway, this is just ideology, but from the technical point of view, the fact that you discover this additional direction means that there is an approximation involved in part of your physics, which is what I would call the continuum approximation from few to many degrees of freedom, that is very different from the H direction, the classical approximation. The two things may have, they have to do with each other, but they are independent a priori, and it's not obvious at all to start with which one has to come first. And we know again from condensed matter that if you're studying the collective behavior of classical particles is very different from the collective behavior of quantum particles, for example. So no reason to expect that the two directions commute, and we have to keep it in mind in our context. So level one already much beyond level 0 of quantum GR, is the view from the pre-geometric atoms of space. So not only space and time have dissolved, but that is in a more drastic sense. Our degrees of freedom are not quantum space-times manifolds or quantum geometries. They are something else. Even the possibility of space has yet to emerge, in the sense of we should still get to the point in which we have some quantum field corresponding to the metric. And the same is for time. Once they have emerged, then we are at level 0. And there we have the standard, we have a quantum continuum description of space and time, and we still have no time and space in the usual sense, and we have the standard issues. But we are at level 1. Now, and we also ask, okay, what should I expect to happen when I move along the n direction to more and more degrees of freedom? Well, one thing that is general is that quantum systems, physical systems, all that we know, if they are interacting, do not have a unique continuum limit or unique thermodynamic limit, the one of many, many degrees of freedom. It depends on the value of coupling constants. The system organizes in different phases. I'm trying to just use generic lessons from theoretical physics, not even specific to quantum gravity. I want to import them in quantum gravity.
You'll notice some of the similarities with what I said this morning.
Sorry?
There's some similarities between what string theorists are thinking too.
Well, no surprise. There's a bunch of clever people in both camps, no?
But maybe this is a hint that we're on the right track, that we're both seeing this importance of large n.
Or that these lessons are obvious.
Indeed. But obvious to who?
Anyway, in fact, I don't see any specific reason to have different camps in the first place.
Neither do I.
Okay, so for a non-spatial temporal quantum gravity system, what are the macroscopic phases? This is a new question that these approaches are starting to address. We need to find at least one where smooth geometry is a good effective description. So what is the right phase of geometric physics? In which phase does space-time emerge? There are recent progresses in these approaches, and I don't want to, again, go into details, but already at the kinematical level, people have started realizing that there may be different representations for your quantum system in loop quantum gravity and in group field theory. And if there are different representations, different phases, there are going to be different phase transitions between them. Again, this is just generic, general lessons, without even going into details. And the real issue is to prove that dynamically you reach the geometric phase in the full quantum theory, not just to assume it or go kinematical. Kinematical is not enough. Okay, also here there has been recent progress. I only mentioned one because I will use the picture later on. I said you can apply standard renormalization tools to group field theories, even though they are very peculiar quantum systems from the point of view of physics and space-time. We are talking about the atoms of space, but formally they're just field theories. So in particular, we started applying functional renormalization group in the full Wilsonian spirit. And we derived, in a very simple toy model to start with, we just derived the flow equations, solved them, numerically, of course, and plotted the phase diagram. The macroscopic phase diagram of this very simple system indeed shows two phases. One is the degenerate from the geometric point of view phase, is a standard symmetric phase, and the other is a broken or condensate phase. By the way, the system ends up being basically that of a 3D scalar field theory on space-time. It's not very different. But that's because the model is very simple. Anyway, so you have two phases, and one is a condensate phase. And the other is more trivial from the point of view of possible geometric interpretation. The internal scale that labels the flow of the renormalization group would be, if this was a geometric model, coming from full loop quantum gravity, would be something like a volume scale for the universe. Okay, so let me now come to the issue of emergence of space and time. I have to reach yet level 2 and level 3. I can do it. I don't know if you all can, but in case, just shoot me. So emergence, by definition, I would say, and I'm using it in the physics sense, not in the philosophical sense of theory reduction. From the physical perspective, emergence has to involve the appearance of properties that are novel with respect to the different description, what we would call more fundamental description of the system, and then robust enough to be, trustable. And here I'm just taking Butterfield, and I learned a lot from Nick and Chris, and so on. And it also requires some form of approximation, some limiting procedure, in order to unravel the novelty of the description. Okay, that's the point I wanted to make here. And of course, it's more difficult to characterize the notion of emergence in a space-time free context, simply because we're not used to it. And here, what I define to be emergence of space-time is just to an approximation or limiting procedure that leads from non-spatio-temporal or not obviously spatio-temporal degrees of freedom, quantum gravity degrees of freedom, to a continuum space-time and continuum dynamics for it. Again, not very fancy. And as I mentioned earlier, there are two limits involved, and it's a matter of specific examples and theoretical contexts to say which one should come first. So, before I go to the other two levels about the problem of time, let me already give away the three levels for the emergence of space and time. One is obvious, from quantum space-time to classical space-time. The degrees of freedom are the same, just one are just quantized. And I would not call this emergence of space-time, just not radical enough. It just is the difficult problem of quantum classical transition, but the issues are very similar to what I would have in the classical theory, okay, plus the fact that I have superposition, but this is really the issue of quantum to classical. But the degrees of freedom are the same. But if continuum spacetime and geometry are obtained from different discrete or non-geometric structures, the issue that you have to address, the question that you have to answer is, you believe that these new structures are physical? If they are, and they're not just regularization tools or something like that, then you're at level one. You really have the problem going from atoms of space to continuum, maybe still quantum space-time, approximately. This is what I would already call emergence properly. But then you have the other issue. If there are different phases possible, then you're at level two. From the atoms of space to continuum space-time, not only is possible only approximately, but only in some regime of your coupling constants and your dynamics. Otherwise, you will go in a different phase that has nothing to do with space-time. Level 2. And this is emergence plus. Or minus. I don't mean, you're going down in levels, so it's fundamentality maybe. Anyway, it's just another sense in which you have emergence. But if the atoms of space are physical and can organize in different phases, aren't you compelled to believe that the other phases are physical as well, even though they're not geometric or not spatial-temporal at all? I think the answer is yes, but then you're at level 3. You have to go from atoms of space to continuum, still quantum space-time, approximately, or you may go to something totally different, which is as physical, a priori, than space-time. Unless you bring in your metaphysical prejudice. Fine, it's not the job of the... I try to steer away from that. This is emergence plus plus.
I'm sorry, what's the difference between that and 1? What's the distinction?
Sorry?
What's the distinction you're making between 1 and 3?
Between 1 and 2.
And 3. 1 and 3.
Well, there is level 2 first,
okay.
There are different phases possible.
Okay, that I get.
And the difference between 2 and 3 is that you do interpret the other phases as well, beside the geometric one, as physical. So something that should be physically realized potentially in the world. Okay, level 2 about time. So if there is a non-trivial quantum gravity phase diagram, I would say that space and time are even more dissolved than they were at level 1, because there's no single path from the atoms of space from the n direction to space-time. So not only there is an extra direction, but it's not even unique, the path. But this implies that in a very strong sense that the atoms of space do not and cannot have a spatial-temporal property themselves. I just want to anticipate what I mean here is the rebuttal of the usual counter-argument. Oh, but if, yeah, you may have something that doesn't look like space-time, but at some point it gives space-time, so there must be some some basic, say, extension property for your atoms, some spatial-temporal attribute that you just didn't bother exploiting, but it becomes what becomes space-time in the end. Well, if there is only one phase possible, I can maybe hold this view. But if there are different phases, it's the same atoms with the same attributes that just organize in a totally non-spatial temporal way in the other phase. I don't see why I would call any of the attributes spatial temporal. Okay, all this rests on assuming the physical reality for the atoms of space. Now the idea of geometrogenesis that will bring me to level 3 about the problem of time, and then I conclude. Then I'm done. I have like 10 minutes?
Yeah.
And 12?
9.
So in the 1 minute I'm losing my asking
Yeah,
questions.
so I think it is a few
Okay, anyway, so 10 minutes are fine. So, if there is a non-trivial phase diagram, there are phase transitions, period. But the question is, okay, then you need to have at least one phase transition from a non-geometric phase to at least one geometric phase. Just following the logic. And this phase transition is what is fancily called geometrogenesis. It has been called in this fancy way by other people before me, so I don't play guilty. But I do play guilty for using it shamelessly to impress friends. And non-friends alike. Now, if the atoms of space are physical, and the different phases are physical, is geometrogenesis a physical process? Is it something that happens in the world, or has happened, or could happen in the world? If it is physical, what physics does it capture? And the hypothesis that people have put forward, and when I say people, I mean me, there's a bunch of other people. Again, I don't want to really play as the only guilty party in the story. But, I mean, a very natural and compelling and tantalizing hypothesis is that you can give to the space transition a cosmological interpretation, by which I mean that you suggest, modestly, that this geometrogenesis is what replaces the Big Bang singularity in a full quantum gravity context. It's just a working hypothesis, so you keep going, doesn't work, doesn't work. So just as a gas would condense into water or a fluid, similarly you have a bunch of quanta of space that pictorially represent as simplices, for example, or spin-network vertices that condense into a still quantum but smooth space-time with fluctuations and so on, but with standard degrees of freedom, collective degrees of freedom. Plus, well, this is what replaces the singularity there. Here I really couldn't find a good way of representing the idea. Something weird goes on there.
I use the flying spaghetti monster at that point in my public talks.
Yeah? Okay, great. So we're on the same boat. We're very crowded on that boat. Very hard to give any pictorial interpretation of this sort of stuff. Anyway, what I like even about this general picture is that, well, the universe, if you know about cosmology, is just a sequence of phase transitions. What I'm saying is just that there is an initial phase transition from a non-geometric quantum gravity phase to a geometric one. Only that. Okay, and there are some, here I just want to do some advertisement, just that all this is not blah blah and following the general logic, and we actually work. So I'm a theoretical physicist, I'm not a philosopher. So I'm not only, by which I mean I'm not only or particularly concerned with the conceptual aspects alone, I come to them from the mathematical models. That's the only thing I need, all my respect. So there is a recent line of research in group field theory and group quantum gravity that is inspired by this general perspective, and it indirectly supports this cosmological interpretation of the geometrogenesis. And it is one concrete example that I know, in a very limited context, in a sense that I will explain, of the emergence of space and time up to level 0, so up to quantum GR, in full quantum gravity, in a formalism that pretends to be just the full definition of the theory. So the hypothesis I said is that the geometrogenesis is a phase transition and that corresponds to a condensation, more technically, of the group field theory building blocks, the atoms that I mentioned at the beginning. So the first problem one has to face is to identify the specific quantum states in the fundamental theory that may have some approximate continuum space-time interpretation. This is basically close-grained. It's the problem of finding configurations of the fundamental degrees of freedom that collectively, in some approximation, can be described, at least kinematically, as a continuum space-time manifold and geometry. And the second problem is to extract, for these states, an effective dynamics from the fundamental theory. And the solutions, the partial solutions that we have in this line of research is that you can show that the group field theory condensates, quantum condensates exactly from textbook condensed matter, just applied to this formalism, have a consistent interpretation as continuum, quantum, homogeneous spaces, all the type that you use in cosmology. So very simple quantum geometries, but continuum quantum geometry nevertheless. It's a very specific class of infinite superpositions of spin atoms. That's why they are continuum states. They do encode an infinite number of those discrete fundamental degrees of freedom, with all sorts of approximations and simplifications, but they do contain an infinite number of degrees of freedom. That's what allows you to interpret them as continuum. But they're very simple. They are described by a single collective wave function. Just like a Bose condensate is described in the simplest approximation by a single wave function which gives you the aerodynamics, the Gross-Pitaevsky wave function. Wave function is a bit of a misnomer for an obvious reason. You're doing aerodynamics, not standard quantum mechanics, but formally it's really the same. In this context, the wave function we obtain is a function on the space of continuum homogeneous spatial geometries, that is mini-superspace, like in standard quantum cosmology. At the dynamical level, you do, again, you keep following the first two chapters of the book on Bose condensates, and you don't go farther because it's more difficult. And I'm still learning. So you really follow the standard analysis and how you extract the simplest type of hydrodynamics for this Bose condensates, for these condensate states. You have various approximations, but what you do is to take the class of states you have chosen, plug it in the fundamental dynamics, in this case the Schwinger-Dyson equation for the field theory, and extract under additional approximations and assumptions an effective dynamics. In this case, what we obtain, so the analog in group field theory of the Gross-Pitaevsky hydrodynamics for BEC is a nonlinear extension of quantum cosmology, of a quantum cosmology equation for this collective wave function. So this is like extracting quantum cosmology in a modified form from the full quantum gravity theory. Okay, level 3, which is time in the geometrogenesis scenario, and in 3 minutes. And there are just many new questions and very few answers. No answers. So, you started by asking, can the cosmological phase transition be a physical event? And be the Big Bang, for example. What replaces the Big Bang in the quantum gravity theory? You say, oh, that's super cool. And as far as cocktail parties are concerned, that's enough. But the point is that a phase transition is moving from a region of the phase diagram of the theory to another one. But can we evolve in a temporal sense or in a dynamical sense in the quantum gravity phase diagram? Can we give a temporal or at least a dynamical characterization of the evolution in the phase diagram of quantum gravity? So can we physically evolve, even if we start from the geometric phase towards the cosmological phase transition? If you cannot give this type of rewriting, then in what sense, you go towards the early history of the universe, where you would find the Big Bang, here you find the geometrogenesis. And this opens really a can of worms a kind of interesting opportunities for philosophers and physicists alike. So recall that we are already at level 2. There's no continuum space, there's no time variable, no time direction. We have pre-geometric degrees of freedom. But we have a phase diagram with two phases, at least. The system is going to be much richer than that. Let's say the simplest truncation, just two phases. A condensed phase, which is this one here, and a symmetric or degenerate phase here. How do we move from one to the other? So the question is, we need some form of background independent no ideology, just really, we don't want to introduce any space-time because we're supposed to show you how space-time emerges. So it should be still a non-spatial temporal evolution of the quantum gravity coupling constants. There is obviously a clear solution, a clear way out to all of this, which is the recent one that Lee has been taking, Lee Small and other people. There is a time, and the coupling constants are a function of time. Okay, fine. I'm not going along that way. There may be reason, maybe different variance is only an artifact in some approximation. The fundamental theory is Java-Lifshitz or something else with some preferred time direction. Okay, it's not my theory in this context. So you need to define some sort of evolution across theory space, from a macroscopic theory to macroscopic theory. And there are three related problems. Unlike all the contexts in to which we're used, there's no external observers that is there in the lab tuning the coupling constants. We know that. That's true also in GR, right? When we say, we have to find internal degrees of freedom, it's exactly because there's no external observer that tell me what time is, space is, and so on. The obvious issue is the timelessness of quantum gravity and GR. But let me point out that there is another timelessness, which is the way we deal with statistical field theory. The fact that when we say that there is a phase diagram, we do not describe tuning the coupling constant as a temporal process, although in the lab we do tune the coupling constants in time. So, last slide. One possible strategy is to try to push the relational formalism one or two levels down or up. Try to devise a relational account of the RG flow. Some proto-temporal interpretation of the RG flow parameter, the scale in terms of which the constants run. And let me sketch one possibility that if you want a temporal interpretation, the internal degree of freedom that you use as a scale for your renormalization group flow should also be the internal degree of freedom that in the relational perspective you use as time to label evolution of your geometry. So the sketch would go a little bit like that. You have a cosmological evolution in terms, say, of the universe volume as an internal time, which you can do it, but the same volume may define the scale for quantum gravity in your RG flow, and then you can show tentatively that, there's a possibility, that a speculation better, that the RG flow towards small volume just brings you towards the phase transition. Supposing the flow here is something like going to smaller and smaller volumes. and then you reach the phase transition. Then from the point of view of the geometric phase, then what you did was just to follow the evolution of the universe to earlier and earlier times, to smaller and smaller volumes of the universe, and where you usually would have a Big Bang singularity, in this theory you would have flown to the phase transition. Just speculation here, but it's recorded, so now it's too late. Okay, so there are many new questions, and the new questions are mainly, well, there are many technical ones. To realize anything like this picture are just questions for the theoretical physicists, but it will need a lot of input from philosophers in clarifying our concepts and sort of guide us or correct us when we are going misguided. And in a sense, it's also related to the issue of writing a covariant and relational version of statistical mechanics, which is a very difficult problem in itself and totally unsolved. So I'm just adding problems as I announced. So at level 3, we have really new ontological issues. So if space and time are emergent, are they real? So we may end up from the picture in which for a good ontology you need space and time, to a picture in which there's no way a fundamental ontology can have space and time in the picture. And what is the ontological status of the other phases, or even just the other regimes of your atoms of space, your quantum gravity building blocks? And can you, philosophers,